Hi folks, Chris McClure. We're going to now discuss quadratic models, meaning we are going to use quadratic functions to model certain situations that we would encounter in life. And we're going to go through some examples of creating an algebraic model based on the physical situation, and then we'll at the end take a look at looking at a scatter plot of some two variable data and then fitting a quadratic function using the regression function on the calculator. Alright, so let's go ahead and dive right in here and start talking about building quadratic models from verbal descriptions. Now, last section in 4.3, we talked about revenue models, where revenue is basically the money that a company brings in from its business. And it's going to be the price per unit times the number of units sold. Now, suppose that for this particular company, widgets, that the number of units sold, X, is given by 1,500 minus 30 times the price. So the number of units sold, X, is a function of price, P. So we're going to answer some questions here, these 4 questions in particular. First of all, we're going to come up with a model that expresses the revenue as a function of price. Now, here we've got X as in the number of units sold as a function of price, but revenue is number of units sold times price, but X is equal to 1,500 minus 30p. So you plug 1,500 minus 30p in for X times P, and you get negative 30p squared plus 1,500p. Now, one of the things that we always want to know about any function that we're dealing with is what is the domain? What is the set of allowable inputs? In other words, what is the range of prices that we could have in order to have any sort of revenue? Now, it doesn't make sense for us to have negative revenue. So we're going to assume that the revenue is positive. Also, the number of units sold, X, is going to be non-negative. So in order for us to have non-negative revenue, we would want the factor 1,500 minus 30p to also be non-negative. So we'll set that 1,500 minus 30p to be greater than or equal to 0 and solve for p. And of course, you know how to solve inequalities. You just move the 30p over to the right-hand side and divide both sides by 30. And you'll have that p is less than or equal to 50. So what does that mean? Now, p must be greater than or equal to 0 here. And in order for X to be greater than or equal to 0, we need for P to be less than or equal to 50. So it's going to make sense then for us to say is that the price must be between 0 and 50 for the domain for this function. Okay, moving along here. What price will maximize the revenue? Well, remember how from the previous section we were able to find the p coordinate. Remember, in this case, p is the independent variable. We're able to find the p coordinate of the vertex. Also notice that this revenue function has a negative leading coefficient. So the graph is going to open downward. So there's going to be a maximum value. That maximum value is going to occur at the vertex. And of course, you plug in the numbers from this function here, plug in the numbers, and that works out to be P equals 25. As in, when the price is $25 per unit, the revenue will be maximized. All right, moving along here. So when the price is $25, what would that revenue be? Well, evaluate the revenue function, which is this function right here, at 25. As in, plugging in 25 for P. There and there. And that's what you see here. And of course, you combine all these numbers, and that works out to be $18,750. So $18,750 is the maximum revenue, which happened when the price was $25 per widget. All right, we have a few more questions. How many units are sold at this price? Now, take a look at the equation, the function that relates the price and the number of units sold. It's this function right up here. Now, if you were to plug in 25 for P, then you'd have 1,500 minus 30 times 25. And that works out to be 750. So we can answer the question, how many units are sold at the price of $25 per unit? Well, the answer is 750 units are sold. If we wanted to graph the function for the revenue, here's the revenue function right here. And of course, we could plot that. We can stick that into our graphing calculator and plot it. It's just a downward opening parabola. And remember, right here is where the maximum revenue occurs at P equals 25. We have our last question. What price should widgets charge to collect at least 12,000? Well, okay, where's 12,000? 12,000 is right across here. So as long as we're between, some values of P that we're going to solve for, then the revenue is going to be above 12,000. So at what price is the revenue equal to 12,000? So set the revenue function equal to 12,000, and then use your algebra skills to solve for P just like we're doing here. So, we're going to factor out 30 after we simplified and factor the resulting quadratic function, and you get P equals 10 or P equals 40. So this tells us that when P is between $10 and $40 per unit, then the revenue will be at least $12,000. Okay? Any questions? All right, moving along to our next example here. Suppose that we are going to plant this garden in a rectangular plot. We need 1,600 yards of fence in order to do this. So that means that the perimeter of this rectangle, which is 2x plus 2y, is going to equal 1,600. And the question is which dimension should we have? What is the length and the width should be in order to enclose the most area? So think about what we've got. We've got the perimeter being equal to 1,600, and we know that the area of a rectangle is the length times width. Now, we have two equations with two unknowns. Now, for the second equation, this second equation is acting kind of like a constraint. We can take this second equation and solve for one of the variables. For example, we could solve for w. You take this equation here, the 2x plus 2w equals 1,600, divide both sides by 2, and then solve for w. Get w is equal to 800 minus x. And then into the area function, replace w by 800 minus x. And now you have area is equal to x times 800 minus x, which simplifies to negative x squared plus 800x. And now you've got a second degree quadratic function. And we know what to do now. We know how to maximize area by finding the x coordinate of the vertex. You see this negative leading coefficient? That means that the graph of this function is going to be a downward opening parabola. So finding the vertex means that we're going to maximize the area, as in the whatever this function value is, which is the area. So find the x coordinate of your vertex, like we know how to do, and that works out to be 400. As in, the area is going to be maximized when the length is 400 feet. And if the length is 400 feet, what does that say about the width? 800 minus 400 is 400 as well. So the width is also 400. So the garden plot should be 400 by 400. Not feet, though. I said feet. It's actually in yards. Yards is the units. Okay, now let's move on to the next example here. We use second degree polynomials to model projectile motion, like we talked about from the previous section. Now here we've got this beautiful little quadratic function which models the height of your projectile as a function of distance traveled, where x is the distance. And here's this quadratic function here. So when you've gone, say, x number of feet downrange, then this function will tell you what the height is above the water. We have several questions to answer, and folks, this isn't all that hard, because we know how to deal with second degree polynomials. Notice that this leading coefficient is negative. You get negative 3200 over 400 squared. So we know that the graph of this function is going to be a downward opening parabola. So we need to find the x coordinate of the vertex in order to maximize this function. So again, find the x coordinate of the vertex, and of course we know what to do here. Negative b over 2a, and just simplify that expression. That works out to be 2500. As in, 2500 downrange, 2500 feet downrange, the projectile will be at its maximum height. And what is that maximum height? Well, plug the 2500 back into this height function, replace x by 2500, and that works out to be 1750 feet. So the maximum height that this projectile achieves is 1750 feet, and that's going to be at the 2500 foot mark downrange. We got some other questions. How far does this projectile travel before it hits the surface of the water? Now, when you get to the surface of the water, the height is going to be 0. So what you're going to do is you're going to set your height function equal to 0 and then solve for x. So you're going to solve a quadratic equation, which you know how to do. Use the beautiful quadratic formula here, plug in the numbers, and you slug through the arithmetic and you actually work out the two solutions. And of course you will discard the negative solution because it doesn't make sense to go in a negative direction. You're only going in a positive direction downrange. So you accept this answer here, the 5,458 feet, as the distance horizontally that the projectile travels before it hits the ground, or the water in this case. Okay? All right? There's the graph of this projectile, where right here is where the cannon is, firing from 500 feet above the water. And here's the projectile of the cannonball and then it hits the water. Boom. And you look at this horizontal distance on the x-axis. That works out to be about 54, 58, right about there. And notice here for that maximum height, that works out to be 1,750 feet. When you're at about the 2,500 foot mark on the x-axis. All right, so this is a very plausible graph. All right, so now if you really wanted to, and I've showed you how to do this a couple times already, how to find the maximum or minimum value of a function, you could just use the maximum function on your graphing calculator to find if you were to graph this on your graphing calculator and hit the minimum or the maximum function, you can find out where that maximum occurs. You could also find out the x-coordinate of this where the parabola hits the x-axis by using the root function or the zero function. All right, we have yet another example. Golden Gate Bridge. I have been across it many, many times when I used to live out in California. I've sailed under it. I've driven over it many times. I've flown on it, flown over it several times in small and large aircraft. And I have special memories of it. My grandfather helped paint it back in the 30s when it was being constructed. So that's kind of dating me a little bit, but that's okay. So let's take a look at it. I mean, I would probably beg to differ on some of these details, but they're roughly correct, though. We've got 746-foot tall towers, which are 4,200 feet apart. The bridge is suspended from two huge cables, more than 3 feet in diameter. The 9-foot wide roadway is 220 foot above the water. Of course, that depends on the tide and the water level, of course, from the tide, but that's okay. The cables are parabolic in shape. Well, roughly parabolic. There's a different term that we'd call it catenary, but that's beside the point. Let's just assume that they're parabolic and call it good. And they go down almost to the surface of the road. So for the purpose of this problem, we'll assume they go all the way down to touching the surface of the road at the center of the bridge. So, and we're going to take a look. Imagine if you were standing right where the cable comes down and hits the road and goes back up again. Imagine from that location you were to walk 1,000 feet down the bridge and you were to look up. How high would that cable be? So let's take a look at what the picture tells us here. Here's a section of the Golden Gate Bridge. Here's the two towers there. The towers are 4,200 feet apart. So if you were to set up a little coordinate system, you can have the y-axis going vertically through where the vertex of that parabolic arch is. And then, of course, half of the 4,200 is 2,100. So you go you go 2,100 to the left, 2,100 to the right to get to your two towers. And so we're told that the towers are 746 foot tall. All right, now if you factor in the 220 feet above the water, all right, then take a look here. That means that the tower, each tower is 526 foot tall above the roadway, because this total distance is 746. So 746 minus 220 is 526. Now we're going to model this arch, this parabolic arch, using this equation here because of the fact that the vertex is right at the origin according to our coordinate system that we've set up. So all we need to do is figure out what A is. We can figure out what A is by using this coordinate 2100, 526, as in when X is 2100, then the Y coordinate would be 526. So you plug in those two numbers, just like we see there, and then you solve for A. And of course, you could simplify it if you want, or you could just leave this as an exact number, just like that. And then write your equation of the parabola, just like you see there. Just understand, though, that 526 over 2100 squared is just a number times x squared. That's the equation of your parabola, which models that parabolic arch. So now, if we want to answer the question, if we go downrange 1,000 feet from where that cable had bottomed out, what is the height of the cable? Then all you need to do then is just plug in 1,000 for x in this equation, and then solve for y. And of course, that works out to be 119.3 feet after you simplify this expression here. Okay? Any questions on that? All right, now let's talk about coming up with a regression equation, a second order polynomial in particular, which would model some data. All right, now what we're talking about is if you create a scatter plot and your data looks like this, or like this. So you upward facing or upward opening parabolic shape or downward opening parabolic shape. Either way, we're looking for an equation in the form y equals ax squared plus bx plus c form, where a would be positive in the first case and a would be negative in the second case. So how do we do it? Well, pull out your graphing calculators and plug in some numbers here. Let's see, these numbers right here, what do we have here? Farmer collected the data given in table 3, so here's the table, for various amounts of fertilizers used, X. So the fertilizer used is going to be X, and the yield is going to be the Y variable. Now, I've already showed you how to input data into your graphing calculator. So I'm not going to show you this time. I'm trying to keep these videos as short as possible. So go into your stat menu in your graphing calculator and plug in all these data pairs. And then go to stat plot. And your viewing window you should have X minimum at -5, X maximum at 45, Y minimum of 0, Y max being 25, and use the X scale and Y scale both being 5, and make sure you delete any equations in your equation editor. See if you could reproduce the stat plot on your graphing calculator. And then go to your statistics menu and go to statistics and then try to find your quadratic regression equation. I'll show you real quick. You go in your statistics menu, go over to calculate, and go down to quadratic regression, which is option 5. And then it'll take whatever's in your L1 and L2, and it'll treat all these numbers as X values and treat all these values in L2 as your Y values. And then when you, back in the home menu, after you had put in quadratic regression, and it'll come up with an equation. Of course, my data was not the data that was on this example, but I showed you the keystrokes there. Okay? And it'll give you a value for A, B, and C. Okay? So you should get numbers just like this. So folks, I want you to pause this video right now, plug in these numbers right here into your statistics edit menu, so you can edit L1 and L2. Plug in these numbers here, the fertilizer amounts for L1, and plug in these yield numbers for L2. And then do the stat plot, and then do the quadratic regression, and see if you can get this function. And so if you were to truncate after about 4 decimal places, then you could write your quadratic function just like this. So you see here. This function will tell you the predicted yield as a function of the fertilizer used. So you tell me the fertilizer, and I'll put that in for X there, and simplify, and I could predict the yield. This function will do that. So then what you could do is input this function here, this regression function, into your equation editor and plot that right on top of your stat plot. And then, like I said, you can use that regression function, this guy right here, to predict yields for given values of fertilizer, or even vice versa. If you tell me the yield, I could use this function to tell you how much fertilizer that you should use as well. Okay, so that's it. Of course, you have problems to work on. Make sure that you're reading the textbook as well. I'm going to post the homework. And folks, no need for me to remind you, but I'll say it anyway, is the homework is going to be, going to get a new homework assignment each day. And not only that, you've got your midterm exam to take. And I've already gotten results from a handful of people already. Friday is the deadline. Please don't push it and wait till the last minute to do it. Meaning, if you're planning on taking it Friday afternoon, and then, oh crap, what happens if your car breaks down or you get sick or something on Friday afternoon? So it's better for you to take it earlier rather than later, because I will not accept tests after Friday. Okay, plain and simple. All right, so having said that, please let me know if you have any questions about anything. If not, have a good day, and I'll see you in the next section.